I'm very excited that we have Dr. Romain Schotter from the University of Strasbourg in France. He just received his PhD in August on precision measurements of multi-strain baryons at the LHC with the Alpha experiment. So congratulations.
Thanks.
In addition to data analysis, he worked on the pre-alignment for the new inter-tracking system analysis for IPS2 for service work. He served as the French ambassador for the juniors committee in Alice. And he held a leadership position in his PhD student association in Strasbourg. So today, Romain's going to talk to us about precision measurements in the multi-strain baryon sections of that.
Yeah, it's a long title.
Please go ahead.
But thank you very much for the introduction and for the invitation. I'm really excited to be here with you today. So today I'm going to talk to you about precision measurement in the multi-strain baryon sector at the LHC with the ALICE experiment. So today's talk is basically divided in three parts. So after introducing the topic, I'm going to briefly present the experiments I've been working in, namely the ALICE experiment, as well as the identification of the particle of interest here, the multi-strain baryons. Then I will move to the second part of the presentation, where I will present the two precision measurements I performed. So the first one consists in a highly precise mass measurement of multi-strain baryons in order to test the fundamental symmetry of nature, which is a CPT symmetry. And then I will move to the second measurement, which studies the coordinated production of strange hadrons in order to shed more light on the origin of the so-called strangeness enhancement in proton-proton collision. And then I will move to the third and final part of the presentation, where I will try to summarize what we learned from these two precision measurements, and I will try to discuss what could be the future precision measurements using multi-strain baryons. So let's start with the introduction. So as you all know, nature can be described by four interactions. So you have gravity, electromagnetic interaction, strong and weak interactions. Me, I'm primarily interested in the strong interaction. And within the framework of standard model, the strong interaction is described by quantum chromodynamics or QCD. So basically in QCD, you have two kinds of objects. So you have the quarks, which are basically one of the basic constituents of ordinary matter, and you also have the gluons, which are the force carrier of the strong interactions. Together, the quarks and the gluons are the partons, and they have in common the fact that they share a color charge. So in the same way as an electron carries an electric charge, the quarks and the gluons carry a color charge. And what makes the strong interaction interesting is the fact that the gluons, the force carrier of the strong interactions, carry a color charge. And because of that, they can self-interact, and this self-interaction is as a consequence of the shape of the potential, and in particular, it is responsible for this linear term in the potential. So basically, you can see that this linear term grows with the distance. So basically, if you consider a pair of quarks and anti-quarks, and you try to pull them apart, basically their energy will grow with the distance until we reach the point where it becomes more energetically favorable to create a new pair of quarks and anti-quarks. And at this point, the pair of quarks and anti-quarks will just break into two new pairs of quarks and anti-quarks. This is the color confinement regime, where the quarks and the gluons are confined within hadrons, so either a baryon with 3 quarks or a meson with 2 valence quarks. But in this potential, you also have a second term, which is a Coulomb-like term, which dominates at high energy, or equivalently at small distance. And in this limit, we reach the asymptotic freedom regime, where the quarks and gluons are confined. So this picture actually gets more complicated because actually here you can see the coupling constant of QCD, alpha S, which depends on the distance or equivalently the energy. And here you can see in the middle plot the running of the coupling constant of QCD as a function of the energy. And basically you can see again the two regimes. So you can see at high energy, you are in the asymptotic freedom regime and the coupling constant is small. It is sufficiently small actually to use perturbation theory, and therefore in the asymptotic freedom regime, strong interactions can be described using perturbative QCD. But now, if you go down in energy, the coupling constant increases, and you reach again the color regimes. So in this regime, the coupling constant is too large to still use perturbation theory, and you have to resort on non-perturbative techniques to describe strong interactions. And so in the color confinement, the strong interactions can only be described by non-perturbative QCD. So these are basically the two regimes, and ordinary matter as we know it is basically made of hadronic matter, so we are in the color confinement regime. However, it is possible to move from this confinement to the deconfinement regime, either via heating the matter, so either by increasing the temperature, or by compressing, so by applying some pressure. But one way or another, in the end, our hadronic matter will undergo a phase of transition towards a new phase of deconfined and thermalized particles called the quark-gluon plasma. This transition typically occurs at around 154, 155 MeV, which corresponds typically to 100, which is typically 100,000 times hotter than the temperature of the sun. So also, it is believed that the QGP is one of the primordial state of the universe in the first microsecond of its existence. So if you want to study the QGP, unless you can time travel, the only way to study the QGP is either by observing neutron stars, or you can also try to recreate it in heavy ion colliders. So in heavy ion colliders, you can experimentally try to recreate it in laboratory by colliding heavy nuclei at extremely high energy. At such energies, actually, your nuclei looks like two pancakes. And here you typically have the typical scenario of heavy ion collisions. So after a equilibrium phase, the energy density is high enough, your system will undergo a phase transition toward a phase of deconfined and thermalized particles called the quark-gluon plasma. But because of the initial boost of your two nuclei, the system will grow. The size of the system will expand. And because of this expansion, the energy density will decrease, which will cause a decrease in the temperature. And this decrease, so the system will decrease in the will experience a decrease in temperature until we reach the chemical fusion temperature, where our QGP will evaporate into a gas of hadrons, and it will evaporate into a gas of hadrons. Temperature of the system will continue to decrease until we reach the kinetic freeze-out temperature, where our gas of hadrons will just fade into free hadrons that can fly toward our detectors. And here you can see a typical display of ALICE of the heavy ion collisions, where you can see all the particles that are being reconstructed. This scenario typically takes 10 to the power minus 23 seconds, so that's very short, and due to this fleeting lifetime, the QGP can only be studied based on the remnants of the collisions. So the QGP is typically characterized by different signatures. Here's just a subset of them. We can mention, for example, the energy loss of high momentum QCD objects like jets, which are created during the pre-equilibrium phase. So these objects will experience the medium and will lose energy inside it, which will lead to the phenomenon of jet quenching. We can also mention, for example, the collective flow of soft particles. So basically, this is created by the pressure gradients due to the initial asymmetry of the collision, such as this, which forces the particles to fly in some preferred directions, as illustrated here. So, and this collective flow of particles is typically can be described by hydrodynamics. Or we can also mention the enhanced relative production of strange hadrons, also called strangeness enhancement. So here, this is basically an enhancement of the strange hadron production with multiplicity. And when I talk about strange hadrons include different kinds of particles. It can include the particles, basically it includes a particle which contains at least one strange quark. So it could be a particle with a zero net strangeness number, like the phi meson. It can also be a particle with one strange quark, like the K0 short of the lambda. Or it can also be a particle with more than one strange quark, which are called multi-strange baryon, which are, for example, the psi minus and the omega minus, which contains 2 and 3 strange quarks, respectively. Okay, so nowadays, basically the QGP has been studied for more than 20 years now, and nowadays the experiments that study QCD and QGP physics are all located either at CERN or at Brookhaven National Laboratory. So at CERN, you have the Large Hadron Collider, the RHIC, and at Brookhaven National Laboratory, you have the Relativistic Ion Collider, the RHIC, but I guess you all know this. And what I will present to you today has been done in ALICE. So it's one of the experiments installed on the ring of the RHIC. And now I just would like to say a few words about ALICE. So ALICE has been in operation since the beginning of the RHIC. So it has been in operation for the run 1 and run 2. So from 2009 to 2018. And almost 4 years after the end of the RHIC run 2, the RHIC has restarted for a third campaign of data taking in 2022, which is called the RHIC run 3. And during this long shutdown, actually, the hardware and software of ALICE have been fully upgraded to fulfill two objectives. One is to improve the spatial resolution of the tracking system. The second is to increase the data taking rate. And with these two objectives, it is clear that ALICE with the RHIC run 3 intends to step into a precision era, or let's say, quote unquote, precision era. I say quote unquote because actually, if you look to previous measurement from the RHIC run 2, there was already plenty of precision measurements, especially in the light flavor sector. We can, and this precision measurement takes the shape of either highly precise measurement, such as this one, which is a highly precise measurement of matter-antimatter imbalance at the LHC, or it can also take the shape of a more multi-differential measurement. So here the idea is more to map the problem to try to decorrelate all the effects. And here I can, for example, mention the study of the strange hadron production inside and outside the jets, or we can also mention the separation of initial and final state effect in the multi-strange baryon production. And today, what I will present you today is in line with this objective. So the idea is to pursue this precision endeavor with multi-strange baryon using the LHC Run2 data. So basically, to that end, I perform two precision measurements. One is a high precision mass measurement of the sign omega minus and their psi particles. And the second one is a correlated production, is a measurement of the correlated production of strange hadrons. And before I talk a bit more about this precision measurement, I would just like to say a few words about ALICE and the identification of the multi-strange baryons. So ALICE during the LHC Run 1 and Run 2 was made of 19 detection systems. I will not talk about this 19 detection system today. I will just discuss the one I use in my measurements. So starting with the innermost detectors, so I use the inner tracking system, the ITS1, which is made of 6 layers of silicon detectors, 2 layers of silicon pixel detector, 2 layers of silicon drift detector, and 2 layers of silicon strip detector. And together, all these layers can be used to reconstruct tracks and vertices, but also to provide trigger information as well as a multiplicity estimation at bit rapidity. I also use the time progression chamber, which is also called the TPC, which is a gaseous detector. So basically, it is a drift chamber filled with a gas, so either neon or argon. And basically, when a track traverses this gas, it ionizes the gas and we can detect the created electrons. And in our case, in our measurement, the time progression chamber, the TPC, is used to reconstruct tracks, but also to provide some particular identification information based on the energy loss of the tracks in the gaseous medium. I also use a time of flight detector, the TOF, which is also a gaseous detector, which in our case is used to provide PID information based on the time of flight of the detectors, but also to reject some specific type of pilot called out-of-batch pilot. And finally, I also use the V0 detectors, which are 2 arrays of scintillator detectors, one located on the A side of the detector called V0A, and one on the C side of the detector called V0C. And together, they can be used to provide trigger information, but also multiplicity estimation at forward rapidity. And now, before I move on, I would just like to talk a bit more how we plan to measure these multi-strange baryons. So throughout the whole presentation, the Xi and the omega will be studied in their characteristic cascade decay channel. So basically, the Xi will decay in a baryon and a lambda, and then the lambda will further decay in a baryon and a proton. The omega follows a similar cascade decay topology, except that here it's not a baryon but a kaon. So you can imagine that looking at this plot, if you want to reconstruct a Xi or an omega, basically what you have to do is associate 3 charged particles. But actually, if you try to do this, here you have an example of an event display in ALICE of a Xi decay in the detector. You can see that the whole challenge of reconstructing a Xi or an omega is to identify the correct association of 3 charged particles from this huge combinatorial background. And to distinguish the true Xi or omega from this combinatorial background, we are going to use what is called the topological reconstruction. So the idea of the topological reconstruction is to make use of the characteristic cascade decay topology of the Xi and the omega. So the idea is to apply a set of 14 geometric and kinematic selections in order to identify the correct topologies. So for example, we could require that the distance of closed approach between 2 tracks is small if they originate from the same decay. Or we can also require that the Xi decays at a certain distance to be a Xi actually. So this is this kind of selections typically. And to further reduce the combinatorial background, we also apply some PID cuts based on the TPC information for each decay vectors. And now with that, I finished with the introduction. So now I will move to the work I did during my PhD. And I will start with first analysis, with first measurement of the mass of the multi-strange baryons. So I will start with an introduction on this measurement. So as you know, the standard model was initially built upon the invariance of the discrete symmetries of charge conjugation, parity transformation, time reversal, and the combination of these 3 discrete symmetries, the CPT symmetry. You also know that the strong and electromagnetic interactions are invariant under all these transformations. But the charge conjugation, the parity, and the CP symmetries are violated by the weak interactions, as demonstrated by Wu and Goldhaber experiments in the 50s and Cronin and Fitch experiment in 64. And so the T symmetry is also violated. So among all these discrete symmetries, only the CPT symmetry is conserved in the end. So this conservation has two consequences. The first one is that particles and antiparticles share the same fundamental properties. So it means that a particle and an antiparticle should have the same mass, the same lifetime, and so on. But also that particles and antiparticles are created in pairs. And this last statement is actually in contradiction with astronomical observation, because as you know, there is a matter-antimatter imbalance in the universe. Of course, the CP violation could explain this matter-antimatter imbalance, but it turns out that the CP violation is too small to fully account for this matter-antimatter asymmetry. So this is why we need to look for additional sources of symmetry violation, including, for example, a CPT symmetry violation, as it is done in the string theory or in some standard model extension. Nowadays, the most stringent test of the CPT symmetry involves the K0 K0 bar mixing process, which allows to put an upper limit on the mass difference and the lifetime difference between the K0 and K0 bar at the level of 10 to the power minus 19 or minus 18. So for sure, it will be very difficult to compete with the precision, with such a precision with this indirect test. But if we just focus on direct test of the CPT symmetry, we can see that there is still some progress to be made for some mass difference measurement, in particular in the multi-stage baryon sector. So here you can see two screenshots of the PDG mass difference values for the psi on the left and the omega on the right. And you can see that the previous mass difference measurement of the omega and the psi is of the order of 10 to the power minus 5 and relies on a relatively small statistics. You can see that it relies on roughly 2,000 psi and roughly 6,000 omegas. But also what is impressive is that the world value for this mass difference relies on only one measurement. Now, we can also try to have a look at the mass values of the psi and the omega, which are presented here on the left for the psi and here on the right for the omega. And we can see that here we can basically make the same observation. We can see that the previous mass measurement for the psi and the omega relies again on small statistics, roughly 2,000 psi. And for the omega, you can see that base case scenario, we reach 100 omega. And these numbers, you should maybe try to put them in comparison with what we have at the LHC in the run 2 with Alice. So if you combine all the proton-proton collision at a center of mass energy of 13 TeV, from the LHC run 2 recorded by Alice, you get roughly 2.5 million psi and roughly 133,000 omega with little background. So it is clear that here there is a window of opportunity to provide new mass values and maybe even improve better mass values for the psi and the omega. So that's basically the idea of this measurement. So the idea is to use the Alice detector to first provide new mass measurement of the psi and the omega, and second, use this new mass measurement to compute the mass difference value in order to test the CPT symmetry. So now I would like just to explain you how we plan to measure this mass. So to measure the mass, we need first to separate the signal and the background candidates. And to do this, we are going to use an inline mass analysis. So basically, here you can see the inline mass spectrum of psi minus. And the idea is to separate the signal and background candidates by fitting the inline mass peak with a triple Gaussian, which is simply the sum of 3 Gaussians. And the background will be fitted with an exponential function. And from this fit, we can measure the center of the inline mass peak, which is given by the mean of the triple Gaussian. And this will be our estimator of the measured mass. But from this fit, we can also identify what is called the peak and the background regions. The peak is in red and the background regions are in gray. And from these two regions, we can estimate the raw signal of our candidate. And we can see that for the psi, we get a purity of roughly 95%. Of course, we can do the same thing for the omega, and this is presented on slide 19. And here you can see that for the omega, we reach a purity of roughly 91%. All that I presented here is done in real data. So this is true collisions, and this is the mass of true candidates. But now we can also try to do it in simulation in Monte Carlo data. And this is particularly interesting in our case because it allows us to evaluate what are the global performances of our procedure of our mass reconstructions. In particular, what we want to do is we want to compare the reconstructed mass here and the injected mass, which is often the PDG mass. So here you can see the extracted mass of the psi minus in simulation And here you have the injected mass in simulation, which is the PDG mass. And we can see that here, for example, the measured mass in simulation does not necessarily agree with the injected mass. Here, typically, you have an offset of 15 kV. There could be different origin to this problem. It could be due to a problem during the data reconstructions. It could also be due to a bias in our candidate selections, like maybe we got too tight in some cuts and maybe it's biasing our mass. Or it could also be due to a problem in the mass extraction, like we are not using the correct fit functions or things like this. In any case, I mean, we did not manage to identify the origin, but in any case, this effect is a small effect. And for most analysis, it's not a problem. But in our case, since we want to do a precise measurement of the psi and the omega, this kind of offset, we need to take it into account. So this offset in Monte Carlo should be taken into account in the final results in the end. So here I've given you all the ingredients you need if you want to reproduce the analysis. So here you have the procedure to measure the mass. And now just to give you an idea of the complexity of such a measurement, here you basically have the list of all the systematic uncertainties we had to study. And today I will not bore you with this list. I will just focus on one systematic uncertainty, which is related to the stability of the results and the dependence on the decay radius. So today I will just try to give you a glimpse of the complexity of such measurement with this specific systematic uncertainty. So here, what we want to do is that we want to check that the results are stable and do not fluctuate over time, space, momentum, and so on. And to help us or guide us in this quest, basically we're going to use a candle, or in our case, we're going to use 3 candles. We're going to use the lambda, anti-lambda, and K0 short to help us to identify where our mass measurement is stable. So the reason why we focus on these particles is because their mass are known very precisely. We know their mass with a precision of 6 keV for the lambda and with a precision of 13 keV for the K0 short, which is typically the targeted precision for our measurement. But also what is particularly interesting is that the lambda, anti-lambda, K0 short decays in the characteristic V0 decay channel. So basically the lambda fly over a certain distance before decaying a pion and proton, and the K0 shorts follow the same cascade, the same V0 decay topology, except that it decays in a pi plus and a pi minus. And this is particularly interesting because it displays the same displaced vertex topology as a cascade. So we can reconstruct the characteristic V0 decay topology using the same procedure, somehow the same topological selections. And so the objective here, in what I will present, is to extract the mass of the lambda, anti-lambda, and K0 short, as it was done for the psi and the omega, and check that their mass stays stable over time, space, momentum, and so on. So here I will focus on the dependence on the decay radius. The reason for that is that there could be some momentum miscalibration in our measurement. And this momentum miscalibration could originate from an imprecision of the magnetic field, or it can also originate from imperfect energy loss corrections. And in the latter case, if that's the case, it should be seen via dependence on the decay radius. And here on the left plot, you can see the measured mass of lambda and anti-lambda as a function of the V0 decay radius. And on the right, you can see the same thing, but for the K0 short. And you can see here that there is a huge dependence on the decay radius. Basically, you can see that the mass increases by 500 keV for the lambda, almost 1 MeV for the K0 short, which suggests that indeed there is a huge problem with our energy loss corrections. Well, actually, there are 3 problems that I will try to explain you. The main cause of this dependence is coming from the event reconstruction. So basically, in ALICE, when you finish the event reconstruction, when you finish to track your tracks, the tracking algorithm ends at the outer wall of the TPC. And what you want to do in the last stage is to propagate or extrapolate your track parameters to the primary vertex, or more precisely to the distance of closest approach to the primary vertex. And during this propagation, we are going to apply energy loss corrections. The reason why we apply energy loss corrections is because we want to take into account the fact that the particle loses energy each time that it traverses some material. So if the particle is flying in the detector, so in the outward direction, each time that the particle traverses some material, it's supposed to lose energy. So you should subtract energy to your track parameters. But here we do the opposite. Here we do an inward extrapolation. So here, instead of subtracting energy, we should add energy. And this is what is represented by this green cross. And if you just stop at the secondary vertex position, since it is a secondary track, here you should have applied the correct amount of energy loss corrections, and you should be fine. But since we want to extrapolate our track parameters back to the DCH, the primary vertex, we continue to apply extra energy loss corrections, which end up to extra energy and therefore extra momentum to our track parameters. Of course, here I'm just talking about tracking. Here we just try to reconstruct the tracks, not the V0 and cascade decay topology. So when you want to reconstruct your cascade or V0 cascade decay topology, you need to extrapolate your track from the primary vertex to the secondary vertex position again. But during this last step, it turns out that we do not apply energy loss corrections anymore. So the extra momentum that you had before, what you added before, is still present, which leads to a bias in momentum and therefore a bias in the mass. So this is the main cause of this mass shift, but there are also a third and second issue related to how we compute these energy loss corrections. So basically, the energy loss corrections in ALICE are given by the Bethe-Bloch formula, which is indicated here. And this Bethe-Bloch formula depends on the mass of your particle. And therefore, you need to make an assumption on your mass of your particle. And during the tracking, we take the most probable mass given by the PID of the TPC determined during the track. However, in the bottom left corner plot, you can see the fraction of K0 short lambda, anti-lambda, psi minus, psi plus, omega minus, and omega plus with the correct mass hypothesis. So all the decay daughters with the correct mass hypothesis. And we can see that in most cases, the wrong mass is considered. Basically for the lambda, you can see that in at least 60% of the cases, we apply the wrong mass hypothesis. And of course, if you apply the wrong mass hypothesis, you will miscalculate your energy loss corrections, and this will turn into a bias in momentum and therefore a bias in the mass. And there is a third reason, which is still related to this Bethe-Bloch formula. So there are other parameters which are more related to the parameters of the material. And actually, if you look in the tracking analysis, we make some assumption on the materials we have in the detector. So for example, if you try to reconstruct a track in the TPC, you assume that all the material in the TPC is made of neon, that is the gas present in the TPC. And when you try to reconstruct a track in the ITS, we assume that all the material is made of silicon, including the beam pipe made of beryllium, the support made of carbon, the cooling, and so on. And of course, because you apply the wrong material hypothesis, you will again miscalculate your energy loss corrections, which will turn into a bias in momentum, and therefore a shift in the line mass. So
yeah, sure. If you use Giant, don't you just then put in all the right materials?
Absolutely, yeah. But we use Giant only for simulations. When you want to reconstruct the event, you don't turn Giant. Okay. You use really the Bethe-Bloch formula to try to have an estimator of your energy loss corrections.
Okay, so in the simulation, use Giant to do the comparison.
Yes, for simulating
all the right material in there.
Yeah.
Okay, thank you.
Yeah, exactly. Yes.
So is it correct that you are trying to measure the mass difference between the particles and their antiparticles?
Yeah. So
would some of these uncertainties or differences cancel out?
Yeah, it doesn't, yes. They will cancel out in the mass difference, actually. You can already maybe try to see it on this plot. You can see that basically the mass difference between each point is roughly the same for all points. Of course, you can see some differences here and there, but it turns out that we will apply other cuts that will solve this issue. It's more actually this shift is more related to a momentum resolution issue. But okay, to put it simply, my answer is that indeed the effect will cancel out in the mass difference.
But you still also want to get the individual mass.
Yeah, exactly. Okay. This effect, what I'm talking about, is only important if you want to measure the mass of your particles.
Mm.
Yeah. So whilst you're halted, questions now,
yeah.
This is cool. But so why was the mass shift of your psi so much smaller than the mass shift of your lambda? Because you had 500 keV.
No, here it's for the lambda and K0 short.
But it's like, well, I would think the psi decays later, just because it's going to do 2. So I would have thought your shift should be closer to your large radius shift. And that's 500 keV. Weren't you at 15 keV for the psi?
But it's not the same thing. Here it's a dependence on the decay radius. And before the mass offset I was mentioning is integrated over the radius.
But if I've gone psi goes to lambda goes to p pi pi, aren't I closer to a large radius, which is where your mass shift was biggest?
Yeah, that's true. But for the psi, it will not be an issue in the end, because it turns out that the effect of the lambda on the psi mass in the end is almost negligible. It's because because in my interpretation, if you look at the invariant mass expression, you have basically the energy of your lambda plus the energy of your pion squared minus the momentum of your lambda plus the momentum of your pion squared. So basically the lambda contributes to the momentum of your, contributes only to moment or to the energy and the momentum in your environments. But actually, if you have a huge, the effect I'm mentioning is an effect of the order of 500 keV, so it's a keV level effect. But in your energy is the square root of p squared plus m squared, and the mass of the lambda is typically 1 GeV. So the mass of the lambda will actually overwhelm the effect, and will not see it.
Because you put in the correct lambda mass.
Yes, yeah, okay, that's true. I did not mention it, but you assume the PDG mass for the mass of the dolphins. Actually, this will be a systematic uncertainty that we also have to quote, because the PDG mass has an uncertainty. So, and this has an effect also on the mass function.
And so my last one was to stop. Like, why was your DDX mass identification so bad? Didn't you say 60% of the time you pick the wrong particle?
It's because, it depends. Because it depends also on the momentum of your particle. You don't have the same identification power for all your momentum. For example, if you are at low momentum, of course, you can easily identify a kaon from a pion. But if you are a decay daughter at, 400 MeV, here you can no longer identify it from a kaon or a pion. So then you just try what is the most probable mass. And then in this case, he is wrong in, I don't know, maybe 50% of the cases. So this is why, we get wrong most of the time.
I should let you carry on, but your K to pi ratio is small though, so don't you mostly guess it's a pion, and then 90% of the time you're right because everything's a pion? Or is that not how Alice's guesswork happens? Because as the kaon goes into the pion, like you said, it's around 500 MeV and so, but it's still mostly pions. Like the K to pi is 10%, isn't it?
That's true, but still, what we want to do, sure, we could assume that everything is made of pions, but then we are wrong. For example, for the omega, the Bethe particle is a kaon. So if we are wrong on this, we are completely wrong on the mass. Or I misunderstood you.
No, okay, that answers it. Yeah, okay.
But again, in the end, all that I presented here is kind of a small effect. It's really not important for most analysis. It's only important for us.
That's cool.
So I guess I'm confused a little, given your answer. If you misidentified a K versus a pi or vice versa, you try both possibilities and then, it will fall out of the mass.
It turns out, yes, we tried for the omega. So, but it's another issue. It's because the psi and the omega, in this case, in their cascade decay channel, so they have a similar topology.
Right.
But we have much more psi than omega. So if you misidentify a psi as an omega, it will be, of course, a background candidate. And of course, if you have much more psi than omega, you will be contaminated by a huge background.
Yeah.
So for the omega, we apply a rejection on the mass rejection. So we take the hypothesis of a psi for, we take an hypothesis for a psi for an omega candidate. And if the mass falls in the mass peak of the omega, in the mass peak of the psi, sorry, we reject it. Yeah.
Okay.
Okay. Okay. So so basically this was the three causes of this mass shift. So again, this is not an important effect for most analysis. But here, since we want to measure precisely the mass, we need to deal with these three problems. And actually, I dedicated a long part of my PhD to elaborate a strategy to correct and remove this effect. So this is basically a three-step procedure called retrocorrection procedure. I will not go into the details, but if you want, we can discuss it later. But now I just would like to show you what we get once we apply these retrocorrections. So here you can see the same plot as before. You can see still the measured mass of the lambda and anti-lambda as a function of the decay radius. In blue, without our correction, and in red with our retrocorrections. And on the right, you can see the same thing for the K0 short. You can see that once we have corrected for these three effects, the mass shift with the decay radius reduces significantly, such that the trend has almost disappeared and follows a quasi-flat distribution. So this is all I wanted to mention with the dependence on the decay radius. So here today, I just wanted to give you a glimpse on the complexity of such measurement, and especially how deep you have to go into the event reconstruction if you want to do a precise measurement. And so if you want to do such a measurement, you have to have a fine understanding of your event reconstruction, but also calibration and alignment and so on. Of course, there are other systematic uncertainties which are quoted in this table. Each of them requires a specific treatment, but I will not mention today. But once we have measured all these systematic uncertainties, we are going to combine them and we compute the total systematic uncertainties given by the quadratic sum of all the contributions. And this brings me to the final results. So in the end, the final results I will quote here are based on roughly 32,000 psi and roughly 21,000 omegas with purity of 96% and 90% respectively. So our results are in this table. So on the left side of the table, you can see our measured mass, and on the right side, you can see the previous measured mass values. Now, just focusing on our uncertainty, and if you compare it to the previous mass measurement uncertainty, you can see that our mass measurement improves the previous mass measurement by 20% for the psi and a factor 10 for the omega. But now, and also you can still on the uncertainty side, you can also see that now our precision is no longer dominated by statistical uncertainty as it was done in the previous measurement. Now we are dominated by systematic uncertainty. So it means that if you want to redo the measurement, but you can, I advise you to do it, it's a nightmare. You will see, you will have to basically have a better detector or better calibration, better alignment. So it's really tricky to have a better mass at this point. And one last thing, actually, if you look at our mass value, you can see that for the omega, the mass value agrees very well with the previous measurements. But now, if you look at the psi omega, at the psi mass value, you can see that there is a huge offset with respect to the previous measurement. It's about a bit more than 200 keV. And this can have some consequences for example, lattice QCD calculations, because the mass of the psi are typically used as some anchor points for lattice QCD calculations. But do not forget that the initial goal of the measurement was not to measure the mass of the particle, but to measure the mass difference value. So here again, you can see our results on the left side of the table, and you can see the previous mass difference measurement on the right side of the table. And the last mass difference measurement had been performed 17 and 25 years ago. And now, once again, if you just look at our uncertainty and you compare it to the total uncertainty from the previous mass difference measurement, you can see that our mass difference measurement improves the previous mass difference measurement by roughly 20% for the psi and a factor 2 for the omega. And now, if you look at our mass difference value, and you can see that our mass difference value is still compatible with 0, which suggests that our results are still compatible with the CPT symmetry. And this brings me to the end of this first analysis, this first measurement. So I will move to the second part, which aims at presenting more the quality prediction of strange hadrons measurement. So here, this measurement focuses on a specific signature of the QGP, which is the strangeness enhancement. So the strangeness enhancement, as I mentioned in the beginning, is one of the key historical signatures of the QGP. So it is the increase of the ratio of multi-strange to non-strange hadron yields with the multiplicity of charged particles produced in the collisions. So here on the left, you can see the ratio of proton K0 short lambda phi sin omega to pi yields as a function of the charged particle multiplicity and mid rapidity. And you can see the strangeness enhancement, which is described by this smooth increase with multiplicity of charged particles produced in the collisions. You can also see that all the symbols overlap, which suggests that there is no dependence on the collision energy, at the LHC at least. And also, you may notice that this enhancement is more pronounced for hadrons with a larger strangeness content. So it is more pronounced for omegas than for psi, which is also more pronounced than for the lambda and the K0 short. But what is striking in this plot is the fact that we observe strangeness enhancement in proton-proton collisions here. And this is a problem because in proton-proton collisions, in small system proton-proton collisions, there is no QGP formed a priori. So historically, this trend in proton-proton collisions has been interpreted by statistical hadronization model. But here we want to focus on a more dynamic picture of the collision. So basically, there are two approaches. There is PTR, which relies on the lone string model. So basically, PTR assumes that in proton-proton collisions, there is no QGP formed, and that the hadronization is only, and the hadrons are only formed by string fragmentation, as illustrated here. Whereas EPOS relies on the core corona approach. So basically, you have the core holding a QGP-like medium surrounded by a corona dominated by string fragmentation. So by design, EPOS assumes that there is a QGP formed in heavy ion collision, but also in proton-proton collisions. So far, both models are improving, and actually they are even converging. But let's see if we can provide further experimental inputs to further constrain these models. So we could, for example, make use of the strangeness conservation in proton-proton collisions. So this strangeness conservation imposes that strange and anti-strange quarks are created in pairs. And this creation in pairs, I mean, this creation imposes, I mean, will lead ultimately to a correlation between final state particles. Just as an example, here you have an example in PTR8 where you can see a QQ bar pair, but will break or fragment, if you want, via the creation of an SS bar pair. And you can see that in the end, this will lead to the correlated production of omega and phi particles. And if you want to experimentally study that, the only way to do it, maybe not the only way, but one way to do it, is to perform angular correlation measurements between identified particles. Actually, talking about this specific correlation, there is a prediction from PTR. So here you can see the omega to pi n yield as a function of the charge particle multiplicity for different PTR configuration. And basically, PTR predicts two things. It predicts that the omega abundancy will increase in presence of a phi meson in the event. So when you go from the black line to the blue line, but also that this increase becomes more and more pronounced when the both particles are produced closer and closer in rapidity. So when you go from the blue to the red line and from the red line to the magenta line. So the goal of this second measurement is basically to test this prediction. And to start with, we need to measure the correlated production, starting with the correlated production of Xi and Phi meson. So we start with this correlation because the Xi are much more produced than the omega. And therefore, we have a much higher statistics. So by starting by this Xi-Phi correlation, we can estimate what is the feasibility of this measurement. And once we are sure that we can perform this measurement, we'll repeat it with the omega-phi correlation. Now, just before I move on, I just would like to mention an important detail. Here, PTR proposes to measure the omega abundancy in presence of a phi meson in the event. So here, the phi meson plays the role of a trigger particle. And it's important that when you have a trigger particle, you have a good control of its purity. However, it turns out that you have a better control. I mean, the purity of the Xi and the omega is much more controllable. So here, in our case, what we're going to do is that we're going to measure the phi abundancy in presence of a Xi or an omega, which is the opposite of what PTR proposes. But it is kind of the same in the end. Now I just would like to explain you how we plan to measure this correlation. So basically, we use this three-step procedure. So first, we want to identify a trigger particle. So basically, we want to look for a Xi or omega cascade decay in the event. And once we have found an event with a Xi or omega candidate, we are going to reconstruct all the phi resonance candidates. So in this measurement, the phi are studied in this K plus K minus in this hadronic decay channel. So the phi being a resonance, it will fly over an extremely short distance, about 46 femtometers, before decaying a K minus and a K plus. And once we have identified our trigger and associated particles, we are going to correlate them. And to correlate them, we are going to form pairs of trigger and associated particles. And basically, we are going to see how the population of the pairs distribute as a function of the difference in rapidity, delta y, the difference in azimuthal angle, delta phi, and if possible, how this population distributes with multiplicity. But if you want to measure this correlation function, it turns out that this is a bit more complicated than simply this. Actually, you need to determine all these terms. And if you want to measure this correlation function, you need to estimate first the raw signal of your phi candidates. So, as I said, the phi resonance are reconstructed in this hadronic decay channel, and it is reconstructed by pairing any primary kaons you can find in the event. And of course, if you just try to pair any primary kaons you can find, you will end up with wrong association, and therefore a large combinatorial background. And to deal with this large combinatorial background, first we're going to suppress as much background as we can. So we need to evaluate the background first and subtract it from the invariant mass in the end. To do this, we're going to use what is called an event mixing technique. So basically, we try to form deliberately wrong candidates. So we take a kaon from an event, and we can take another kaon from another event, and we pair them together. In this way, we are pretty sure to form a wrong candidate, and in this way, we can mimic the shape of the combinatorial background. Then we subtract it from the infinite mass, and we get this infinite mass spectra for the phi. And then we need to separate the signal and background candidates. And to do this, again, we use, we resort to an infinite mass analysis. So we are going to fit the infinite mass peak with a void function, and the background will be fitted with a linear function. And from this fit, we can estimate the raw signal of our candidates, and this gives us the raw signal of our phi resonance candidates. So this is basically the denominator of our correlation function. But there is also a denominator, which is simply given by the raw signal of your cascade candidate. But this was already, I already presented it before. I mean, how we measure the raw signal of our cascade candidate was already presented in the first measurement. So I will not spend more time on this. And just before I move to the results, I will just say a few things on the systematic uncertainties. Here, we just want to have an idea of the order of magnitudes of these uncertainties. So here, at the moment, we just focused on the most natural and certainly dominant sources of systematic uncertainties, which are the systematic uncertainties related to the cascade and resonance identification. So to quantify these systematic uncertainties, basically what we did is that we varied the set of selections, and we observed all the results changing under different set of selections. And you can see here basically the results, systematic uncertainties in percentage due to the cascade selections, and the systematic uncertainties due to the resonance selections here on the right table. And this brings me to the first results for the psi-phi correlation. So here you get, so this psi-phi correlation has been measured in minimum bias events. So this is roughly integrated over multiplicity, but you also measured it in high multiplicity events, which correspond to the top 1% highest multiplicity events. So here you can see the psi-phi correlation as a function of the distance in rapidity on the left, and you can see the same thing as a function of the distance in azimuth on the right. In minimum bias event, in a full symbol and open symbol for high multiplicity event. So let me try to guide through these plots. So basically here, if a data point is above 1, it means that the phi production increases in presence of a psi candidate. If a point is below 1, it means that the phi resonance production decreases in presence of a psi candidate. And if the point is aligned with 1, it means that the phi production is unaffected by the presence or not of a psi candidate. So just focusing first on the correlation as a function of the distance and rapidity, considering the uncertainties we have in minimum bias and high multiplicity event, we can see that there is no observable correlation with the distance and rapidity for the psi-phi correlation. Now, concerning the correlation with azimuth, in azimuth, we can notice that there is an increase in minimum bias events of the phi production by roughly 35% when it is produced close to a psi candidate. And surprisingly, on the away side of the distribution, so when the phi and the psi candidate and the back-to-back configuration, surprisingly, there is no enhancement of the production of phi. I mean, we would have expected a peak, but there is no peak observed. So there is an increase observed in minimum bias events, and if you look at the high multiplicity results, we can see that the high multiplicity results seems to follow the same trend, both for the dependence in the distance in rapidity and the distance in azimuth. But surprisingly, the trend for in high multiplicity event seems to be systematically below the trend we have in minimum bias events. So just to give you an example for the correlation in azimuth, we can notice that in high multiplicity event, we have an increase of 15% versus 35% in minimum bias events. And this seems to suggest that maybe the phi production is less dependent on psi production in high multiplicity event. So it means that basically in high multiplicity event, the strangeness is more distributed in the conditions. So here, this is the psi-phi correlation where we compared minimum bias and high multiplicity event. But we can also try to compare it to QCD-based Monte Carlo models. So we can try to compare it to PITIA Monash to 2013. So this is a default configuration of PITIA. We can also try to compare it to PITIA in its color rope tune. And we can also try to compare it to EPOS. And here you can see again the correlation function, the psi-phi correlation as a function of the distance in rapidity on the left, and the psi-phi correlation as a function of the distance in azimuth on the right. And just again focusing on the left plot first, we can see that all the models we have, so PITIA, Monash, PITIA, color rope, and EPOS, reproduces well the trend with the difference in rapidity. But again, considering the uncertainties we have, there is no way to discriminate one model from another. Now, looking at the correlation in azimuth, we can notice that all the models, at least for the away side, seems to provide the same description and qualitatively agree with this data. But now, if you just focus on this near side contribution, we can notice that PTR seems to overestimate the yield, whereas EPOS seems to underestimate it when the phi is produced close to XR. And this could, maybe we can interpret it by just looking at the difference between PTR and EPOS. So PTR basically relies only on string fragmentation. So it is basically a model which only describes hard QCD process. Whereas EPOS also incorporates some soft component via the core component of EPOS. So in a way, this could be an indication that the Xi-Phi correlation is kind of an interplay between soft and hard hadronization mechanism. But yeah, basically that's it. But from all I presented so far for the Xi-Phi correlation, this only also tells us one thing, that this measurement is at least possible with the Relativistic data. So now we should try to have a look at what we get when we try to perform the same measurement with the omega phi correlation. And this is what you can see here on the left plot for the Xi-Phi correlation. Omega phi correlation as a function of the distance to rapidity on the left, and omega phi correlation as a function of the distance in azimuth on the right. So ideally, we should try to do it in minimum bias and high multiplicity events. It turns out that in minimum bias events, we don't have enough statistics. So here we just have to focus on what we have, so on high multiplicity event. And on the left, you can see the omega phi correlation as a function of the distance and rapidity. And you can see that considering the uncertainties we have, there is no observable correlation with the difference in rapidity. And on the right, you could see maybe a hint of an increase when the phi is produced close to an omega. But again, considering the uncertainties we have, it's difficult to draw any sharp conclusion here. So it turns out that for the omega phi correlation, that's quite limited in statistics. And this actually brings me to the end of this measurement. I will move just to the conclusion. So basically, in what I presented today, I presented you two measurements performed in the Relativistic 2 with ALICE. So the first one was a precise measurement of the mass and mass difference of the multi-strange baryons in order to test a fundamental symmetry of nature, the CPT symmetry. And I showed you that we managed to improve to achieve a 20% and twofold improvement of the precision on the mass different values of psi here and the omega here. And the mass different values are still consistent with the CPT symmetry. Then in the second measurement, I try to show you a measurement of the correlated production between multi-strange baryons and resonance in order to try to understand what are the microscopic mechanisms at stake in the strange particle production. To do that, we perform an angular correlation measurement between identified particles. And basically here we focused only on the double identified particle pair correlation measurement for psi and phi. And I presented you comparison to high multiplicity data, high multiplicity events, and some QCD-based Monte Carlo models, so PTR and EPOS. So okay, so today also to put it differently, I presented you two precision measurements. One was a highly precise mass measurement, which puts into perspective the limits we can reach in terms of detector calibration and detector alignment in the end. And the second is a measurement of the correlated production between multi-strange baryons and resonance, which is a measurement of the angular correlation between identified particles, which in other words is a multi-differential measurement. And this multi-differential measurement puts into perspective the limits we can reach in terms of statistics with ALICE during the Relativistic 2 data. So in other words, this is the best we can do with the Relativistic 2 data for the omega and psi measurement for this measurement. However, as I mentioned in the beginning, ALICE has been upgraded between the Relativistic 2 and RHIC 3. And I believe that with this upgraded version of ALICE, we could overcome this limitation, because in this new version of ALICE, we could have the possibility to have a more accurate calibration and alignment of the detector, but also now we have a much higher available statistics. Just to give you an idea, considering only the data from 2022, we have already 300 times more minimum bias events than in the Relativistic 2. So that's just to give you the improvement factor. And now, so this is the end of what I've done so far. But now I just would like to discuss with you what could be the future precision measurements using multi-strange baryons. Because here what I presented so far is precision measurements of multi-strange baryons, but I believe we can do precision measurement using them. And an example of a measurement for that is maybe to study the charm quark hadronization in a collective medium, so in heavy ion collision, but not only, also in PP and PA collision, because as you know, there are observation of collective behavior in these small systems. So, of course, if you want to try to understand the charm quark hadronization, we should study the charm quark hadronization for charm baryons, and also for charm meson, including open charm meson and hidden charm meson. So we can try first to provide maybe a better understanding on the charm baryon production. So here you have an example of the baryon to meson ratio for the psi 0c and the psi c plus over 0 as a function of momentum. And you can see here that it is compared to different description, macroscopic description via statistical hadronization model or microscopic description with PTI. And you can see that whatever the description you consider, all underestimates data. In particular, if you look at PTI in its default configuration, which is tuned on E plus E minus collisions, you can see that here the trend is completely off, which already seems to suggest that there is something going on in proton-proton collisions. So maybe to try to shed more light on the mechanism at stake in the charm baryon productions, you could try to do something like I presented in the second measurement, like a correlation measurement, where you could try to measure the correlative production between psi 0c or psi c plus or omega 0c and any identified particles, such as maybe starting with the most produced particles, so pions, kaons, protons, and maybe if we can lambda, k0 short, and so on. And with this kind of correlation, we could provide some further experimental constraints to constrain these QCD-based Monte Carlo models. And of course, these charm baryons decays in multi-strange particles in psi minus or omega minus. So if you want to perform this measurement, you need to have a very good, actually an excellent reconstruction of these multi-strange particles. So this is an example of a measurement we could do using multi-strange baryons. So here we basically use multi-strange baryons to better understand the charm baryon productions, but we can also try to use it to provide a better understanding of the open and hidden charm meson productions. Here I will just focus on the hidden charm meson production. So usually in ALICE or even at the RHIC, the charm meson production is essentially studied with the J psi or the psi 2s. The reason for that is that because they are abundantly produced and easy to reconstruct. And it turns out that the ground state of the charm meson state, the eta C, which is also much more produced, is relatively unexplored, experimented. And the reason for that is that because it is always studied in this decay channel, so in 2 pions, and of course, in 2 protons. And the protons being abundantly produced, of course, you will have a large combinatorial background, and this is always difficult to deal with. Here you have the latest measurement of the eta C production in proton-proton collision at 13 TeV performed by LHCb. And to deal with this combinatorial background, basically they had to cut on momentum. So they had to go at high momentum to cut, to deal with this combinatorial background. However, I believe that we can do better. I believe we can go at lower momentum if we make use of the multi-strange baryons. So, for example, what is interesting is that the eta C also decays in this lambda anti-lambda decay channel, but also in this psi plus anti-psi decay channel. And then this is particularly interesting because then if you can reconstruct precisely the lambda or the psi and anti-psi decay, then you can really reconstruct your eta C measurement. And in this way, you have really a very good control on your purity because you control very well the purity of your psi and lambda. And you can really control and pilot the purity of your eta C, and hopefully you could go at lower momentum where maybe this is more interesting. And another interesting aspect on this measurement is that this decay channel is also common to other charmonium decay. It is common to J psi, psi C0, psi C1, and so on. So then you can really redo the whole charmonium spectroscopy and really pave the way towards highly precision exploration of the charmonium spectroscopy using multi-strange baryons. And cherry on the cake, here the J psi also share this decay channel, and this is particularly interesting because the J psi production is very well known. So you can use it as a benchmark to control really what you are doing and control your measurement. So this is an example of what you can do using multi-strange baryons to provide a better understanding on the hidden charm meson productions. And of course, what is also interesting is that you can also push towards new reconstruction techniques, such as the strangeness tracking. So here you can see the upgraded version of the inner tracking system of ALICE, the ITX2, where basically we introduce new layers close to the beam pipe. And with these new layers, we basically start to decay systematically the passage. I mean, we can detect systematically the passage of omega or psi particle. And so we can start to track these particles. And this enables their direct detection before they decay. And this extra constraint on the decay of the omega psi particles help us to identify the correct topologies. Just to give you an idea, here there have been already feasibility studies, and here you can see, for example, what we gain in terms of DCA, distance of closest approach to primary vertex. And you can see in blue what happens and what you gain once you start to track these omega and psi particles. You can see that the resolution, I mean the width of your peak, significantly reduces. Actually, it reduces by a factor of 4 if you start to track these particles. And this is particularly interesting because if you have a better resolution on your DCA, you can better identify who are the correct candidates or not. And so you can reach also better purities and so on. And yeah, basically, this is, I believe, what we can gain using multi-strange variance. And I will finish with that. And I would like to thank you all for your attention.
Thank you for that very nice talk. Do we have any questions?
Thanks for the nice talk. Can you go to slide 42? Right. I was wondering if you have comparison with the models for the high multiplicity event.
No, actually, I don't, because of the problem is I started actually to do it for minimum bias event because it's easier, it's integrated over multiplicity. But then I also wanted to do it for high multiplicity data, but then you have an issue with EPOS. The problem is that EPOS is, compared to PTR, a relatively slow particle generator. Just to give you an idea, to produce just this comparison, it took me a week. And it's not even with EPOS in its default version. Here, actually, I didn't precise it, but I use it, a specific tune of EPOS, which is made for fast simulation. So basically, you do not describe the hydrodynamics of the core in this version. Actually, even if you would like to do the proper comparison, you would like to run EPOS in its default configuration. And if you want to do it, actually, you gain already factor 10 or 100 in terms of computation time. So I do not have the comparison high multiplicity event because simply I did not have the time to run it.
I see.
Because of EPOS, which is a constraining factor.
Yeah, so I was thinking maybe for Pistia, because the data does show a different trend than I would naively expect, because I would think high multiplicity means that you are more likely to have events that have jets, and there could be a peak in the same jet, like as in the phi and the psi produced in the same jet. So I would expect there to be a peak at 0 with higher multiplicity, but the data shows the opposite trend. So I was thinking.
Actually, I was also expecting that initially, but actually, you see, most actually of the strange particle production is not in jets. Actually, there are. I mean, in the beginning of the talk, I mentioned a measurement of the separation of the charm production inside and outside of jets, and actually, it turns out that most of the production is coming from the bulk, it's coming from outside of the jet.
Right, but if you look at angular correlation, what?
Yeah, you would have the contribution of jets because you would have, of course, more separation in angles.
Yeah, so I was thinking the peak compared to the pedestal would be coming from jets. So it's, I guess confusing to me that actually the data.
No, I agree.
Okay.
But I don't know. I don't know more actually.
I mean, I would have expected the other way. I mean, what he sees, and that is that you have so much background production, of these strange particles that the jet part of it in high multiplicity events is just very small compared to min bias, where you're basically selecting out the correlation.
Right, but then wouldn't that give us like a higher pedestal for high multiplicity in general instead of like a peak
Right, that's what I mean. You get a higher pedestal, but then if the peak to pedestal is small in high multiplicity versus min bias, then you might see the peak in min bias, but not in high multiplicity.
So is the pedestal like normalized down to somehow? Trigger particle. Okay, I
This
think
is just the cross section, right? Divided by the number of triggers.
Well, it's the cross section of one given you produce the other.
Yeah.
Isn't it?
Right,
Yeah.
the correlation, yeah.
While we're on this slide, you mentioned here that Pythia is better at getting hard QCD stuff and EPOS is better at the soft stuff. So you might think if you split your trigger and associated particles into different PT bins from like low to high, maybe as you go up in PT, Pythia would get it better.
See it here. Absolutely.
Yeah, did you try this or you're too
No,
statistical?
because again, we are still a bit limited by statistics, so we cannot go this way.
You need Alex
It's a
and
good idea.
I'm free.
Yeah, exactly.
Maybe related point, I was wondering why you narrow to such a small centrality slice, 0 to 1%. Is there a reason for that?
Actually, it's because in ALICE there is a different type of trigger, and there is this offline. I mean, it's kind of it's an online trigger, but basically we only record events which match this, which are basically the top 1% ALICE typically.
Okay, and there's no like 0 to 5% or something.
I mean, it's not a trigger. I mean, of course, you can apply a cut to go to higher multiplicity event, sure, but it's not a trigger, so to say.
Okay.
I would say it's not an online trigger.
I have a question about, I think it's in slide 21 where you have this little grocery list of all sort of sources of systematic errors that you went through, and we only actually looked at number 2. So I'm just curious about this, and we've chatted about this, but I never understood what the actual, I guess, end of the story was with respect to 4 and 5 when we're talking about
Okay, yeah.
with these angles, right? Because
Yeah,
the
yeah,
analytics was a big issue for the longest time.
So I don't have the plot to show it.
I mean, it's fine. I mean, my actual question is like, so in a B0 topology, let's say for like a lambda, right?
Yeah,
So how often
I
do you misidentify, say, because you have a proton, a pion, and then they switch the charges, right? Depending on if it's positive.
Yeah, yeah.
Negative. So how often did you run into the issue where you were misidentifying these and then possibly getting an anti-lambda when it's actually a lambda?
So this actually, I don't know how much time we are wrong on this. But you see, in the end, we also reach a purity of 95 or 90%. So even if we are wrong in not so many cases, if you think about it. I mean, it's only 5 or 10% of the cases. Actually, no, it's even better because I mentioned 95 and 90% for the sine the omega. But for the K0 plot, we reach typically 99%. So basically, we are wrong in 1% of the cases.
So it's just pretty negligible.
Yeah, absolutely. It's what I would assume. And concerning the opening angles, so I don't have the results to show it to you. In the end, there is no difference we observe. So Fernando basically was mentioning this difference. So when you try to reconstruct a decay, usually you consider this case, this simplistic case, where basically your tracks are well separated and the decay point is located somewhere in the middle. But actually, this case is quite is not dominant. In most cases, you are in this configuration where you have 2 possible minimum, and so then you could be wrong in one of the cases, and you need to find a way to properly identify in which cases you are. So of course, if you are wrong between this cowboy and sailor configuration, this could have an effect on the mass. So we had a look at the dependence on the transverse opening angle, and this is interesting because this dependence on transverse opening angle, depending on the sign of the opening angle, can give us if you are in sailor or cowboy configuration. But it turns out that, okay, I don't have the plot in the presentation, but it turns out there is no difference between cowboy and sailor configuration. And concerning the azimuthal angle, so this is another angle that I did not mention. Here are the results actually for the lambda. So okay, let me try to guide you through this. So on the left, you can see the measured mass of lambda and anti-lambda in Monte Carlo. as a function of the momentum of the metal angle. So it's the azimuthal position of the decay point. So the direction of the decay point. So if this is your primary vertex, does the decay happen here or here or here or here? It's not the radius, it's really the direction where your lambda is flat. Here you have the trend in Monte Carlo data, and on the right you have the same thing in real data. You could see that basically in Monte Carlo, it's basically flat with the azimuthal angle. So just to give you an idea, you have a fit probability between 1 and 96%. So basically it's it's well described by a flat distribution. But now if you look in real data, it's kind of a mess because there is large variation going from one angular sector to the next. And this is very problematic because this means that there is something in real data which is not properly taken into account in Monte Carlo simulations. So we try to identify what could be the source of this effect. Just long story short, in the end, the only difference we identified is a difference between where you look at the decay. If you look on the C side, so negative Z positions, or A side positive Z positions, you can see that on the C side, you have still this dependence, whereas on the A side, this dependence is still present, sure, but it's much less pronounced. And it doesn't mean that we know what's happening, but to me, this only means that there is something going on between the A and C side. And it turns out that, in my opinion, what's going on is that there is a problem due to the forward dipole magnet on the C side, which will lead to distortions in the magnetic field, which is not, it should have been taken into account, sure, but who knows? There could be distortions in the magnetic field. We never remeasured it at all. And this could have some influence in your calibration, and therefore it could bias your momentum estimation and could shift your mass from one angular sector to the next. So in the end, we don't know it, but it turns out that this offset will be the dominating systematic uncertainty, which is really just limited by a problem of calibration. Sure. But then again, just to open on this, we could actually try to solve this issue if we reperform the calibration and alignment of the detector. And maybe one way to improve it is to make use, for example, of the K0 and lambda mass measurement. So here we use it as a candle, and maybe you can use it as a candle to calibrate our detector. So this is already done by CB or CMS, where they use the Z decay or the J psi decay as a candle to constrain the calibration and alignment of the detector, basically. So here, but this is not done in ARIS. So what you could do is maybe try to reduce calibration and alignment, imposing that the mass of the K0 short, and why not the lambda, correspond to the PDG mass value. And if you impose this request, for sure it will change the position of the detectors, but also their calibration. And hopefully it could solve this, this trend. Just to give an idea for the alignment, when you try to do the alignment, basically you try to minimize the chi-square. And the problem is that there could be some configuration. You could have two configurations which give you the same chi-square value. And then you don't know which one is the correct one. And your minimizing algorithm does not know it. So here you have an example of that, which is called the RHIC mode, where basically you have the red track like this, which is one possible configuration. But actually, if you rotate one of the detector, you can get this blue track. And this could still be visible for the minimizing algorithm. And so you cannot see the difference between the two. And applying such a constraint could help to remove this weak mode, the alignment and calibration of the detector. Yes.
If no one else, give someone else a chance. Go ahead, Parker.
So I just maybe I missed it on your precision measurement.
Yeah.
Mass. So of course, if something exists, you want to move the mass to 0% error, right?
Yeah.
But what is the other scope of measuring these mass so accurately? What does it really mean?
For the mass, it will not change much. Okay, maybe it will improve maybe the precision of some lattice QCD calculation, maybe. But where it's important to me, it's really for the mass difference measurement between particle and antiparticle. Where here you can really try to test it's a symmetry of nature, which is a CPT symmetry. So for that, this is really what you could gain.
Right, but even at this scale of small errors in the mass?
Yeah, because Okay, it turns out that what we gain is not much. I mean, we gain 20% and a factor 2. But still, I mean, you never know, because you see, if this point was here instead, it means that the CPT symmetry would be broken.
At what point it was there, no? When,
Yeah,
you know,
But you are still within the band of.
Yeah, we are still within. I mean, here this is the band of the previous measurement. But yeah, the 0 is here, the error bar is here, so we are still compatible with.
I have sort of a naive question. Why, I guess, why in one measurement was there so like 20% versus like twofold improvement?
Okay, I don't have the slide for that, but actually, among the different dependents we studied, there is a dependence on momentum. And it turns out that the dependence, I mean, basically what you want to try to see is where we are flat, where the mass is stable with momentum. It turns out that for the psi, you have to cut at higher momentum at than for the omega. Actually, I mean, this makes sense because they have, I mean, it's the same cascade decay topology, but it's still different kinematics because it's not the same mass. One decays in a pion, one in a kaon. It makes sense, but it's not necessarily the same cut. But for the psi, to have a stable measurement, you had to go, I mean, you had to cut tighter on momentum, which result to a higher loss in statistics. And this is what causes this issue. I mean, this lower improvement.
Okay.
So just a comment and a question. I mean, the comment is that it's interesting that you do sci-fi correlations. That's great for one of like Fernando's background slides with science fiction, right? Okay, sci-fi. Aside from that, you know, you mentioned the eta C, which is hidden charm. Now that you've done a lot of studies on the, so that's a future thing,
Yeah.
on the phi, right, which is hidden strangeness.
Yeah.
Now, I don't know that I've seen, in fact, I don't think I've seen any of the measurements of, let's say, phi over pi versus multiplicity, you know, like we see in the multi-strange baryons and all that. So, I mean, am I wrong? Where is that?
I think it has already been done. Here, for example, yeah, it's really the ratio of phi to pions.
Okay, and it's pretty flat,
Yeah.
even from PP,
It's kind of the same
right?
trend as the K0, like the K0 shot of the plot.
Okay, good. That's what I was thinking, but
Yeah.
that's real good. Okay. Otherwise, I have a bunch of things we can talk about.
But yeah, it's still till now for that one, since just talking about this, no models can describe the phi production for all three systems, right?
No, I don't think so. Yeah.
Right, so I think this is still.
Right.
And I
Still ongoing.
you have this really nice picture of the rope or the string breaking, the fragmentation works where the SS bar pairs come from.
Yeah.
And I mean, most of these little generators treat the phi as being string 0, where in principle they cannot be coming from the same string as your picture shows.
Yeah.
Right.
So that's still open, right?
I was wondering about that, you know, because everything else kind of multi-strange and everything goes
Right,
in
and
the
that's just trouble chill.
P and P bar go. Yeah.
Can you go to this, you have this compared to models?
It's this one.
No, the
The prediction.
the colorful strangeness enhancement versus multiplicity one, like the one that you were just.
Okay.
I thought there was one with.
I did too. I thought there was one where you also had momentum, but
Yeah, I think it was like
I think you have it somewhere.
9x. It was compared to Pithy and EP.
Yeah.
Okay. Sorry. Okay, this one. Sorry.
Oh, there's no.
Yeah, there is no file.
Yeah, I mean, and we do
I
that.
think because it's the SMP off. I mean.
Yeah, I mean, in the low multiplicity, and starts doing this thing where it shoots to infinity.
I wanted to follow up on a question that Yoshi asked about the systematics. Did some of them cancel in the mass difference? And if some of them did, then what ended up being like the dominant,
So
like the limiting factor in
yeah.
that measurement? So
So,
I guess naively, I thought maybe some of them would cancel and you would maybe benefit.
okay, so that's for the mass, it's not for the mass difference. But it turns out that the dominating systematic uncertainty comes from this last one, which is actually it's due to what I mentioned before. So we measure the mass in real data and in Monte Carlo, and the offset what you observed in Monte Carlo, we record it in real data. But of course, the mass that we measure in Monte Carlo also has an uncertainty. And this uncertainty is quoted as a systematic uncertainty, which is this one. But since we as I mentioned before, we need to cut tighter for the psi and for the omega on momentum, then you lose statistics. And this loss of statistics is reported, it would be quoted here as systematic uncertainty, and this would dominate. So let's say all the effects cancel out, but in the treatment of how you cancel them out, you lose statistics which lead to a higher uncertainty. So somehow you still, the uncertainty is still cancelled out, but it comes back behind you.
I see. Okay, thank you.
Go one slide farther. I just kind of noticed an interesting trend, I thought, with time. This is chronological, right? And it kind of started, at a lower mass and it goes up. I don't know, why that's the case. And the very early measurements were low. And did techniques change like in 1970? It's almost like there are two trends there.
Did the lambda mass change?
Oh,
Yeah, that could be.
I actually had a similar question about, do you know why there was such a long gap between that 1975 measurement and the 2006? What was going on?
This actually, I
decades.
don't know. Well, actually, I guess it's because there are much more statistics.
Yeah.
Usually in these measurements, they don't have a lot of statistics, maybe 100 psi, possibly. Here, they are using basically the data from Delphi. So it's E plus E minus, and they use like 2000 psi, which was, I think, an improvement by a factor 10 or 100 maybe.
Yeah, it's interesting because it's kind of the opposite trend that you expect, and that is between fixed target and colliders. Usually you have less statistics, right? But then here you see that gap is between fixed target and colliders, and you have much higher precision at least.
The result's going to change the average.
Yeah, actually, well, actually, maybe I should discuss that a bit.
They should already lied too.
It's not yet published, so. But we can have a look maybe at the. Okay, let me start. So.
Oh no, I'm just asking.
It's a bit complicated how the PDG works actually. So the PDG quotes always two numbers. It quotes what is called the PDG fit. Basically, they make a fit of the data, and the world PDG average, which is the world average. But they do not consider all the data all the time. For example, for the psi, you may have noticed that maybe the band here of the PDG matches exactly the uncertainty on the measurement. It's because there the PDG just use the last measurement as the world value. And this is why actually our difference is maybe not so worrisome in a way, because it could be that their measurement was wrong. Or it could be that ours is also wrong. It's possible. But it could be that there is also wrong, and maybe we should just take the world average value, which is now, I tried to compute it, and this is what you can see here in this orange band. And you can see that in the end, we still keep the same, let's say, ordering that we had before, but the precision has been reduced by a factor almost 2. That's the same. Then for the omega, that's a bit different. Here they decided to take all the data for the fit, or for the world average. And here you can see that in the end, our measurement falls well in the measurement.
So maybe just Yoshi asked this question early on. She didn't quite ask this question, but to me, it was getting at, so you see this close correlation in the sci-fi at small azimuthal angle difference. And then the question that I don't think was asked, but she was thinking, if I may, was whether that's more likely in jets, right? Whether you can just go and look and see if you had that being the case more often in jets than anywhere else, right?
Absolutely. Yeah. But then that's another degree of multi-differential
Statistics.
measurement.
Yeah.
It's another component, but for sure, this is what you should do.
But if you make that in a jet, you're now going to make yet another strange particle. Because a 5 psi leaves me with some S quark floating there. Trebly strange particle jet.
Well, that could be 4, 2 more strange particles there, but
Well, you're going to conserve strangeness.
Yeah, but actually, yeah,
as long as you conserve strangeness, that's all I'm saying.
But that's fine, but to conserve it, psi-phi leaves me with an S quark left. No.
yeah, but you see, that's already
Even unless-
that's also the case here actually, because here when you do still stay on the psi-phi correlation, when you produce this one psi, in any case, in this particular example, you also produce a psi plus.
Right.
So you should also have this psi
Right,
plus.
you could have this particle correlation.
So you already have this issue in our measurement.
Yes, right.
It's not a problem specific to jets.
But if it's produced thermally, then the psi minus the psi plus don't have to be going in the same direction, right?
Yes.
Right.
So that's the thing with jets, so they would all have to be.
Yeah, that's true.
But have people looked at this? Like at Quark Radar, Alice was showing the measurements of not multi-strange as you're using things, but multiple strange particles in an event. And I was not showing the probability to produce 1, 2, 3, 4, and there's 1, 2, 3, 4. Have you tried just doing it sort of a combination of multiple amounts of strangeness?
No, actually, I tried to at some point to look at how many multi-strand. For example, here basically in most events you have just one reconstructed psi particle, but you could have 2 or 3 psi reconstructed particles in the event. But actually, each time that you add a psi particle or omega particle, you pay a factor 100 in terms of statistics. This is what I observed.
Right.
So in most cases, we only manage to reconstruct 1 of them, not 2. And sometimes there are even 3. But I never seen any event with more than 3 psi particles.
Maybe not psi, because Alice is showing them for up to many strange particles, right? I think it was beyond.
But I think the one for quark matter was for the epsilon 3 data. Yeah,
Could be.
I think so.
It was data though, not prediction.
Yeah.
Any more? Okay.
Yeah, so I'm gonna switch gear a little bit and ask like a very original question, simply because Helen has been asking me this question myself. And you don't know the answer. But yeah, when you say okay, you see like strange enhancement, and then you claim okay, this is a signature of the QGB. So how does the logic flow from okay, we see here's the spectrum against the number of participants, and how is that like exclusively a sign from the QGB and not like something else? Yeah.
Would be actually the sign of something else. Like initially, we also believe that there was no QGP form, it was just hadron gas. Actually, you can compute also what is the strangeness enhancement for an hadron gas. But it turns out that if you want to have strangeness enhancement in an hadron gas, you would need a lifetime for the hadron gas, which is much longer than what we actually measure. So this cannot be, at least this enhancement we observe cannot be due only to hadron gas component. So in the current state of the art knowledge of this QGP, of this strangeness enhancement, we still interpret it as a sign of QGP, basically. But indeed, this is still an open question. We could always argue that maybe it's not a sign of QGP, because if you observe it in small system, maybe it may mean that we never observed it in QGP.
Any more questions? Okay, Dr. Lord, thanks.